3.6, derivatives of logarithmic functions. So, let's start out with something basic like this. You want to take the derivative of a log base some number of x. Well, one way to think about this is call it a name like y. Y equals log base a of x. Now, what I'm going to do is a little algebraic trick, make a the base of both sides, and both sides of the equal sign become the exponent. So really what we're looking at is a to the y equals a to the log base a of x. Now, a to the log base a of x, think about that, log base a of x is just saying a to some number is going to give you x. But we're taking a to that number. So, what do we get? Well, this must just equal x. So that is a to the y equals x. A to the y equals x. Now what we want to do is take the derivative of both sides. Say that's derivative in terms of x, d dx. Well, on the left side, that we know how to deal with that. That is a to the y times natural log of the base number, a. But keep in mind that this y is a function of x. So we're really chain ruling this, and really what we're doing is implicitly deriving the left side. So that just means we need the derivative of the inside function y, which we're just calling y prime. Now the derivative of the right side is 1. Alright, now let me move everything but y prime over. So this is just 1 over a to the y natural log of a. But keep in mind, this a to the y, earlier we said that equals x. So what we've got is y prime equals 1 over x ln a. Alright, got that one. Now if you think about what the derivative of natural log of x is, it is going to be the same thing, right? But we take the natural log of that base number. But the base number of ln is e. So we're going to get 1 over x ln of e. But ln of e is just 1, so we get 1 over x. Alright, let's see if I can figure out how to delete all this stuff. One at a time. I'm sure there's a better way to do this, but forgive me. Alright, now we want to take the derivative of something like this. Natural log cosecant of x squared. And because the 2 is not here, I'm going to assume that what we need is the derivative of the natural log of the cosecant of x squared. Alright, so I'm going to take, I don't need to do that. I'm going to take the derivative as 1 over the inside function, because remember the derivative of natural log of x is 1 over x. So now the derivative of natural log of something is 1 over that something, cosecant x squared, times, so we're chain ruling this, I need the derivative of the inside function. The inside function, though, that is negative cosecant of x squared times cotangent of x squared. And then finally, derivative of the inside function to x. So notice, got cosecant down at the bottom times cosecant on the top. That leaves me with negative cotangent of x squared times 2x, or a better way to write it is negative 2x cotan of x squared. Alright, how do I get rid of this? I guess I can do that later. Okay, So let's try to take the derivative of this guy. Notice we've got a natural log function and then something inside, whatever that is. So remember, derivative of natural log of x is just 1 over x. So using the chain rule, I'm just going to take the 1 over whatever's inside the natural log for my derivative, except when you take what a fraction, put that, let me say this way, 1 over a fraction, that's really just flipping the fraction. So I'm just going to take 1 over this fraction, but really call it square root of x over x squared plus 1, and then times the derivative of what's inside. But keep in mind, the derivative of what's inside here is using the quotient rule. So let me try it this way. We need low d high, so d dx of the high function minus high d dx of the low function, all over the low function squared, but squaring a square root just gives me x minus 1. Okay, so let's take care of these derivatives. So keeping the outside the same, x squared plus 1. I shouldn't call it the outside function, the function outside the parentheses here. Now we're just dealing with the derivatives. Inside, derivative of x squared plus 1, of course it's just 2x, and the derivative of square root of x minus 1, that is 1 over 2 root x minus 1, and then the chain rule would say, okay, now do it, multiply times the derivative of x minus 1, the inside of the square root, but that's just 1. So we'll leave it. This is x minus 1. Now, how do we deal with this? I don't know. Maybe the easiest way is to distribute this square root in, and notice what happens here is you get a square root times a square root, so that's going to go away, and then when you bring it over to this term, it's going to cancel with the denominator here. So let me write it this way, 1 over x squared plus 1 all over 2x minus, and then we'll have, what, 1 half x squared plus 1 all over x minus 1. Now, this is okay. I'd like to simplify this by taking care of the parentheses here, meaning distribute in this outside factor. And also, we've got a fraction within a fraction, so complex fraction. That's going to be something I want you to get rid of in particular, that is this fraction within a fraction. If you left these parentheses here, I'm okay with that, but don't leave complex fractions here. So, I don't know, to deal with that, if you factor the 1/2 out, you could have this 1 over 2 x squared plus 1 times, now this is the tricky part, so make sure you see this. This is going to be 4x minus x squared minus 1. So I factored a 1/2 out of the top, but that gave me a 4 here. All right, see if you can convince yourself of that. Basic algebra. Maybe I shouldn't say basic. Not so basic. But now we're left with this. The only thing I'm concerned about is if we factor the numerator, could it possibly cancel with the x minus 1 in the denominator? So let me rewrite this. If I factor a negative out so that my x squared is positive and rearrange those terms, I could have 1 over 2 x squared plus, I don't know, let's just distribute that 2 in. And then I factored out the negatives, so that leaves me with an x squared minus 4x plus 1 over x minus 1. And now I might be able to see if I can factor that top a little bit. I don't know, can you think of any two numbers that multiply to be 1 and add to be -4? I'm not coming up with anything. So I think we're done. The other possibility is that something factors to cancel with the x squared plus 1 on the outside, but that is not going to happen either. So, looks like we're done. Okay, this problem is saying differentiate without using the quotient or power rule. We could clearly use the quotient rule if that wasn't one of the stipulations, but even better is we would call this probably x to the negative 2 and use the power rule. So we've got a third way to deal with these. Obviously, maybe not the best way for this particular one, but this is just to demonstrate what you could do if the problem were more complex. So I can take both sides, I can take the natural log of both sides of this, natural log 1 over x squared, and of course everybody remembers their log rules, so this lets me, when I'm dividing inside a log, this lets me take the natural log of the top, and I'm saying natural log, but it really could be any log, log base 2, log base 10, whatever. But then minus natural log of x squared. All right, if I then differentiate both sides at this point, well, notice what I'm going to get when I take the derivative of this first term on the left. Natural log of y, we know how to deal with that now. That's just 1 over y. But of course, implicit differentiation, or chain ruling this, is I have to take the derivative of y, the inside function. Derivative of a constant, 0. And then derivative of natural log of x squared, well, let's use what we know about taking the derivative. This we're going to have to chain rule, though, because the inside function is x squared. So I have to multiply by 2x. So to simplify things, I've got 1 over y times y prime equals negative, and notice we've got an x on top, we've got 2 of them down here, so one of these on top is going to cancel with one of those and leave me with 1 over x, and I shouldn't write a 1 there because this 2 comes on top. Alright, and then to simplify things a little bit more, let me take this 1 over y and move it over. Multiplying both sides by y leaves me with y prime equals negative 2y over x. But of course, the y we could replace by what we know about y. So that gives me 1 over y prime equals negative 2. Now y is 1 over x squared. I've already got an x in the denominator. So if I combine these, I'm going to have x to the third. Just to verify, if we took the derivative using the power rule, what do you get? Well, bring the negative 2 down, call it x to the, now subtract 1 from the power, x to the negative third. Does that agree? Looks like it does. All right, I'll have you do the same thing here. Take the derivative, or sorry, take the log of both sides to start out with, natural log of square root x. But again, using the log rules and calling this x to the 1/2, note that you can take this power down, 1/2 natural log of x. So now take the derivative of the left, take the derivative of the right, and see if you can get down to y prime equals 1 over 2 root x. All right, here's really where this logarithm log differentiation comes in handy. When these quotients begin to look really ugly, if I log both sides, natural log of y equals, and I'm going to skip right to the step of subtracting the two logs, the top and the bottom, e to the negative x cosine squared of x minus natural log x squared plus x plus 1. Now I'm multiplying two functions in here, so really I can write it this way. Using log rules, I can split these up into two different logs, adding them. E to the negative x plus natural log of cosine squared of x minus natural log of x squared plus x plus 1. Alright, so this is looking a little easier. I'm also going to use my power rule for logarithms and bring those guys down. Natural log of y, negative x natural log of e, plus 2 natural log cosine of x minus natural log. Now you can't use the power rule for logs on this last one because we're adding a bunch of stuff. So it's not like the whole argument is being taken to a power, as it was in the other two examples, the natural log of e to the negative x and the natural log of cosine squared. So I can't bring the power down for this last one. Can't do anything with that really. There's no log rules that let me simplify that at all. All right, but now we're going to take the derivative of everything, d dx, d dx, d dx. I'm just taking the derivative of each term. And I'll use the chain rule where necessary, so this is 1 over y, y prime. On the right side now, I can take the derivative, well, keep in mind, natural log of e, that's just 1, so really I'm taking the derivative of negative x, which gives me negative 1. Now I'm going to take the derivative of the middle term, and that's going to give me 2 over cosine of x, because the derivative of natural log is 1 over its argument, but then chain rule it, so times the derivative of cosine of x, negative sine x. So we chain ruled that. Now I'm going to take the derivative of the last term, which is natural log, so I'm taking 1 over the argument inside there. But then chain rule it, so times 2x plus 1. Alright, and so if you were to clean this up, you want to take y prime, move the y over, multiply it over rather, y times negative 1 plus, and I don't know, you can, I'm gonna call this sine over cosine, so try this again, minus 2 tangent x minus 2x plus 1 over x squared plus 1, sorry, x squared plus x plus 1. So the only thing left to do is I'd rather have, give myself some room here, I'd rather have, no, I shouldn't say I'd rather have, I shouldn't have any y's in here because y is defined explicitly in terms of x. So I could rewrite this function y as e to the negative x cosine squared x all over x squared plus x plus 1, and then times everything inside the parentheses. So this was just replacing y, and everything else is going to stay the same. 2 tan x minus 2x plus 1 over x squared plus x plus 1. Leave it like that. Don't try to simplify these log differentiation problems. It can get to be a mess. All right. So I'm just saying here that we didn't actually, we kind of glossed over the idea that when we found the derivative of x to the n, we didn't really deal with the case where n is not some sort of nice integer. We just said, yeah, it could be done. But if you think about this, I'm just going to use the same trick that we've been using in this lesson. Natural log both sides, take the derivative, let's see, can I use another color here? Try to squeeze this all together, dx, oh this is terrible, 1 over y prime, implicitly deriving the left side, and then you can move the n down times the derivative of the natural log of x. We know that's just x. All right, then multiply the y to the other side. So you've got y prime equals n times y over x. But, of course, y is x to the n. So we've got n times x to the n over n. And, of course, over x. X to the n over x is really just x to the n minus 1. Which, of course, is what we knew the derivative was. We just noticed didn't have to specify that n was an integer. N didn't have any restrictions on it, just some real number, and it worked fine here.